Hello friends, welcome. Friend, recently in Indian press there have been a lot of discussion about the government of India's initiative to harness Prasar Bharati's existing infrastructure for implementing a groundbreaking trial of direct to mobile technology in 19 cities. Now, what is direct to mobile? Direct to mobile is reaching the mobile phone via a path which is beyond the cellular network, means circumventing the cellular network. So when you want to receive mobile TV signals in your cellular phones, then you don't have to go through the conventional cellular network, which is basically of 4G and 5G. So you can reach the mobile phone directly using Prasar Bharati spectrum and infrastructure. So that is the concept which is being discussed in the newspapers, and the government of India is quite excited about it. Now, once I saw this discussion, I thought of investigating this issue. So once I investigated, I wrote this article, and this article lists the various challenges which even is being acknowledged by the Secretary INB, because Mr. Secretary INB said, right, if you look at this the quote which I have included in my article, Mr. Apurva Chandra, Secretary Information and Broadcasting, he candidly expressed that there are inherent challenges and we need to overcome those challenges. So I thought it will be better to list those challenges. So you can go through this article. I'm going to embed the link of this article into the description. One of the important challenges for implementing this concept is the integration of the antenna within the mobile phone. So that I briefly mentioned in my article. So apart from various challenges which I don't want to go through in this video, I have already did a video. I'll also embed the link of that video in the description. But let's talk about the integration of the antenna inside the mobile phone. Now, conventionally, all mobile phones, be it 5G, 4G or any mobile phone, they will have the antenna inbuilt into the mobile phones. Now, typically, when you are designing antenna, you have to take into consideration one very important factor, because antenna's capability to receive signal depends upon its size. Now, its size is also directly impacted by the frequency of transmission or reception, because typically when you are receiving signal in an antenna, if the wavelength, which is directly inversely proportional to the frequency, is the antenna is designed such that the wavelength its size is proportional to the wavelength of a certain factor, which is lambda by 4, then the optimal receptions happen within the mobile phone. Means mobile is able to receive signal optimally. Now, lambda is directly linked with the frequency of transmission. As you know, that's the velocity of light is equal to lambda into frequency. Now, higher the frequency, lower will be the lambda. Lower the frequency, higher will be the lambda. For the point of view of mobile phones, because the size is a constraint, you cannot have mobile phones of a certain size than conventionally what we use. So there is a constraint in implementation of the antenna within a mobile phone of a certain size, which is bigger than what we conventionally use. Because in case of direct to mobile, because the targeted frequency is 526 to 582 megahertz, what is happening is that the size of the antenna is becoming bigger than conventional mobile can support, because here the lambda is becoming bigger, and I have explained this in this. Now, in order to further amplify this argument and to basically demonstrate how much is going to be the loss of coverage, I wrote another article which basically is titled by saying antenna size in budget smartphone, the key hurdle for cost-effective T2M implementation in India. So what I am arguing in this article is that budget phone which is getting targeted, because who is going to be constrained or who is going to be benefited from the point of view of circumventing the mobile network for reception of TV? It will be the users who are using the budget phones, right? Because normally those high-end users they don't care, because they actually have the capability to pay for data. Those who are using budget phones, those users are going to be benefited. Now, unfortunately, those users who are using budget phones, the size of the phone that they use, that is the length of the phone and the screen size, is limited because they can't pay for higher screen size because the display will cost money. So therefore, their phones are typically smaller size compared to those users who are using high-end phones. Therefore, implementing an antenna of a smaller size, which is not in alignment with what we need from the optimal reception point of view, which is lambda by 4, will be a challenge and it will lead to coverage loss. So I am explaining this in this particular article, that how coverage loss is going to happen, and I estimate that there will be a loss of 6 dB, which is 75% of the coverage is going to shrink, and making a need for a higher density network, resulting in higher operational cost as well as CAPEX expenses. So that was the point of this article. Now somebody commented in this article saying that it is very easy to solve this problem. How? You can have an external antenna embedded into the earphone, which we use conventionally in case of FM reception. Because in FM reception, you might have seen that people are using FM reception from very beginning. I think I remember that in 2008, when the Nokia phones were very popular, this feature was extensively used, and in India we have a very solid market for SM reception, and people are using it for listening to music, right? On the FM radios, which are already prevalent, the commercial radio services which are already there. So what they do is that because in FM, the frequency band is in the VHF band, which is still smaller, much lower. It's 1/4 of the frequency that we use for conventional D2M network, which are targeting, which is 526 to 582 megahertz. The reception is happening on the by embedding the antenna into the earphone. Means when you are plugging the earphone into the mobile, your earphone cable wire will act as an antenna. So that is the solution which was proposed in this particular case also. Now, when I investigated this issue further, I realized that there will be huge challenges, and therefore I wrote this article. So the purpose of this video is to take you through the challenges that we will face if you try to incorporate an antenna into the wire of the earphone while a consumer is trying to receive D2M, direct to mobile broadcast, using Prasar Bharati spectrum, which is a digital spectrum for TV reception, not for FM reception. So that's the whole purpose of this video. So I wrote this article. You can read through this article, and I'm going to give you a little bit of insight as to what this article is all about, so that you understand and you can have your own views as to what you think about it, and let me know if you in the comment section. So what I'm basically saying is that FM is distinct from ATSC 3.0 technology. Why? Because FM, the whole concept is frequency modulation, whereas ATSC is a digital signal, right, which uses different types of modulation technique, which is QPXK and others, right? It's OFDMA, primarily the frame is of OFDMA, but you can use QPXK, other kind of modulation techniques. So it's a digital, it's a bit level modulation, whereas FM is frequency modulation. And everybody knows how frequency modulation works. I'll show you a picture. So if you have a carrier size and you have a frequency modulated signal, what will happen? Certain frequencies are going to get increased in frequency, certain component of the signal will get increased in frequency, and certain component will get decreased in frequency. You see this? This is a decreased frequency, and then increased frequency. This will be a sign of a, depending upon how the original carrier is, because this is the carrier, this is sinusoidal wave. The original signal is not going to be like this. There will be high frequency component, there will be low frequency component. So they will modulate the carrier. So this is the carrier signal, sinusoidal signal, which will be modulated. And therefore, this is how the FM works. Whoever understands technology and have gone through FM modulation, he will understand it. Now, there is an advantage to this method of working in case of FM modulation, because it is inherently noise resistance. Why it is noise resistance? What it does is it actually amplifies the higher frequency signals more. Signals in the higher frequency get amplified more, and the lower frequency signals actually are not getting amplified, right? So you suppose, let's say if you have a baseband signal which you are trying to modulate, what you will do, it will amplify the high frequency component of the signals more compared to the low frequencies. Since the noise is not getting amplified, what happens is that when you de-amplify or you demodulate the signal, then what happens is that the higher frequency signals which are basically more prone to noise will be better protected. That's the whole concept of FM signal. So what I have done is I have used a concept called pre-emphasis and de-emphasis in FM. You can read through, you can understand that there is a transfer function of 1 plus j. J is basically a complex number. 2 pi f tau, right? Tau is the frame width. And then we have the inverse function. So this is basically doing what? This is modulating the signal in the forward direction, and this is the inverse modulation. So this is how the FM is getting protected from the point of view of noise. So the FM does not get affected by noise. And the other advantage of FM signal is that the signal is of 200 kilohertz of width only versus 8 megahertz versus broadcast signal. So when you have 200 kilohertz signal, the power that you transmit will get concentrated within a smaller bandwidth. So there are two advantages. One is the frequency is lower, which is the VHF band in case of FM, and the power is getting concentrated into a smaller bandwidth of 200 kilohertz, and therefore it can travel much farther compared to a signal which is at higher bandwidth, which is 4 times higher than the conventional. So this is the bandwidth 526 to 582, 4 times higher. And then what happens? The size of the carrier is 8 megahertz, and that's where the power is going to get distributed over a larger bandwidth, and therefore the signal will not travel far. So that is another disadvantage as far as the conventional ATSC signal is concerned. The other important disadvantage is there is a concept called cliff effect. Cliff effect means that as you increase the bit rate, right? Means this is the error bit rate. The error bit rate means what is the bit rate of the error you can tolerate. So as you increase the signal to noise ratio, you will find that the error bit rate is going to get reduced significantly, right? But as the signal to noise ratio gets lower, the error becomes very, very high. What happens is that this is called the cliff. So it falls over from the cliff very, very sharply, because if you look at this particular graph, this is a digital signal which is encoded using a concept called BPSK, right? And that what happens is that there is a sharp fall, right, in the capability of the signal to withstand error, right? As soon as the signals basically becomes of lower signal to noise, because as you go higher, let's say if you have a signal which is of a higher signal to noise ratio in dB, your bit rate is going to be very, very small. But as soon as you go below a certain level, it falls sharply. So what happens is that in case of digital signals, this is a problem which is quite unlike in case of an FM signal. So what happens is that the digital signals are they can tolerate noise to a certain extent. It can't tolerate noise beyond a certain extent if the signal to noise ratio is not configured in such a way that the signals are in this particular area of the curve, so that the bit rate is much lower, error bit rate is much lower compared to what you normally would like to have. So that is the problem with the design of the signal. So what happens is that if you are going to have your broadcast signal received directly on the wired earphone, then there will be a basic problem. The problem would be that there will be interference emanating from outside getting tagged along with the signal, because more the reception surface is from the point of view of antenna, it will catch up high frequency noise which is coming out from outside. So it requires shielding, and that can only happen inside the phone. You cannot have shielding outside the phone because there is no way to enable the shielding in a open wired antenna. So that is the problem, which therefore nobody implements wired antenna, which is loosely coupled wired antenna for these kind of broadcasts. They have external antennas which are properly shielded, earthed, and directed in the direction of the transmission. So you will always see that these networks, the ATSC networks, are typically designed for terrestrial TV reception, which are fixed in a particular direction, and the antenna is directed directly towards the transmitter, which is sending the signal and throwing the signal in front of the antenna. It is not designed for moving networks. That is the concept of these kind of terrestrial transmission. So there will be these kind of challenges you are going to face, and therefore it is not proper to implement antennas directly into the wired earphone receivers, which will act like a receivers, and it will not going to work. And the other problem would be that the battery life is going to drain out significantly, because these antennas are not going to be optimized, and they are going to require high power for reception compared to the FM signals, which are of a much lower bandwidth, and their circuitry is also very simple. Here the circuitry is going to be very, very complex, right? So therefore, that is why I thought of doing this video, to explain to everybody that it is not simple to receive signals using a FM-like concept for digital broadcasting to be received on mobile phones. So the best strategy is to integrate the antenna inside the mobile phone, because then you can have proper shielding, you can optimize the network properly for efficient and optimal reception. But protruding an antenna outside, which is not directed, first of all, it is loosely coupled, it is meant to be roamed with the individual who is just walking, or maybe is going somewhere and maybe sitting in a train or a bus. That is not the way, direct to mobile signals can be received efficiently. It is only possible to receive signals efficiently if it is fixed and directed towards the station where the antennas are pointed towards for good quality reception. Otherwise, you have to create a network which will be so dense that it is going to make the whole infrastructure unviable from the point of view of operational cost, which you can read in my article, where I talk about different types of challenges which you will face from the point of view of higher power usage, etc. will make the network completely unviable. So my point is very simple, that you have got DD free dish, which is giving you 150 challenge. The TV has become very, very cheap nowadays, right? You can get refurbished TV, maybe 2,000 rupees, 2,500 rupees. And TV is a community viewing experience, where people sit down, maybe somebody, sipping tea in a shop, watching TV. Mobiles are more personalized. People use mobiles for video on demand viewing, right? They are not viewing TV on mobile phones, because it is not recorded most of the time. It is transmission which is happening, and you have to tune the transmission. You have to tune your reception time, alignment with the transmission time which is happening. So that kind of synchronous requirement may not fulfill your consumer aspirations or requirement from the point of view of from the point of view of receiving broadcast signals over terrestrial transmission network. So I find this whole concept very, very suboptimal. And why I am so much strongly I am believing that this concept is not going to work, because when I was in Qualcomm, I actually worked in a concept called media flow, and I literally tried to sell that concept, and I failed miserably, because I remember that around 15-20 years back, the TV station Qualcomm basically tried to implement media flow, and the whole concept was completely taken down, and the network has to be unwinded because there was no market for it. The reception quality was very good, and at that time it actually was a much more relevant concept, because the data network was very thin. It did not support those high quality reception for which you needed a broadcast network. But now the concept is completely different. You have got a very thicker data pipe. You can do whatever you want. The network could be engineered more efficiently. There is a possibility to give so much amount of mobile spectrum to operators who want to deploy 5G and 4G in low frequency band. All these things are there. I don't think that broadcast TV using terrestrial network is a concept which is kind of relevant for the times that we are living. this concept is going to not serve any purpose. And given the fact that there is no ecosystem of devices, and these devices, nobody is going to build devices because of the challenges that we have. And the biggest challenge that I wanted to describe is the good quality reception. Because if you have a good quality reception in the mobile phone, then you can configure the network which is much thinner in density compared to what you will require if your phones are not able to receive signals properly. Then your network has to be much denser. Otherwise, putting one single tower and then hoping that the mobiles are going to receive signals is not going to happen, because then that network will become primarily for reception of signals for terrestrial TVs, and we don't require terrestrial transmission network for supporting TVs, which are we have a mature market of DTH, cable, and free dish, DD free dish, for already catering to that. For that, we don't have to replicate that market. So I think that's all, in this video. I thought of explaining this concept so that you understand from where I am coming from. And if you have any further comments or suggestion, and you feel otherwise, I'm very willing to change my opinion, if you strongly believe that this is a concept which is going to work. Because I really don't have any interest, because I got out of job. I strongly believe that the money has to be spent optimally. In my view, if you ask my view, I believe that the spectrum prices for low frequency band has to come down. We cannot basically afford to waste spectrum in 600 megahertz band, 700 and 800 megahertz band. Those spectrum has to be given to the mobile operators on ground for them to deploy 5G services. That's the critical need of the hour today, because 5G without low frequency band is a completely useless service, if you ask me. It does not serve any purpose, especially on the mobile phone, because mobile phone signals have to be received inside the house, and high frequency 3.5 26 gigahertz band does not penetrate inside the house. That's where the focus should be. We should be focusing on that rather than wasting our time and resources and money in these kind of initiatives. Thank you for your time. I'll come back to you later with a new video. Thank you very much.